Hello everyone, my name is Sulal and I'm joining from my home in Napa, California. I'm a research scientist here at Facebook and I've been working here for more than a year now. I work in the data center power management space. I'm joined by my teammates Raghu and Parimala for this presentation. We'll be joining a little later on. Today we'll be talking about data center power outages and how we have built a system called Power Loss Siren to make Facebook resilient to such power outages. First, we'll be talking about data center power outages, then tell you a story about a real power outage that happened back in 2017, which led to many of our users not being able to post or comment on Facebook for several hours. Then we'll present our power loss siren system and explain how it works. Finally, we'll talk about how power loss siren simplifies our data center power infrastructure management. Now let's look at power outages, what they are and why they happen. Typically inside a data center, the power is distributed hierarchically through a tree-like hierarchy of power devices. You can think of power devices as circuit breakers that we have in our home, only that in a data center, it's at a much larger scale. At Facebook data centers, we have three levels of power devices. At the top, we have the MSB or main switch board, which then powers SBs or switch boards, and SBs in turn power RPPs or reactive power panels. An RPP can power an entire row of server racks. If a power outage were to occur on a power device, all the server racks under it will lose power. Such power outage can occur at any level in the power device hierarchy. Larger number of servers are affected if the power outage happens at a higher level. We've also observed that in the past few years, the number of power outages has increased. For example, in the past 4 years, the number of servers that we have in our data center has gone up by 5 times. In the same time, the number of power outages that we are seeing has gone up by 4 times. Thus, power outage frequency has increased as the number of devices that can fail has also increased. There are various reasons for why we might have power outage inside a data center. For example, there could be voltage sags, whereby during thunderstorms, the voltage on a power device might suddenly drop, and there is an inrush current that trips the circuit breaker. Similarly, there could be electrical faults on the power device that may lead to power outages. We also perform regular maintenance on power devices that sometimes don't go as planned and can lead to server power outage. Now let's look at how maintenance failures can lead to power outage. Back in 2017, in Facebook's North Carolina data center, we were performing a maintenance on an MSB that didn't go as planned and led to server power outage. Let me describe how generally MSB level maintenance should have worked. Whenever we need to perform maintenance on a MSB, it needs to be isolated and de-energized. We have a reserve MSB for such purposes. We would disconnect the servers from the MSB. During this time, the servers are powered by in-rack batteries. The servers are then finally connected to a reserve MSB. We refer to this as open transitions. Open transitions generally last between 10 to 15 seconds. And our batteries are designed to power the servers for up to 90 seconds. However, in the 2017 maintenance, things didn't go as planned, which led to server power outages for several hours. And during this entire time, the affected users could not post or comment on Facebook for several hours. Now, Raghu will be describing how power outages affect services and can have user visible impact.
Thank you, Sulal. Hi, everyone. My name is Raghu. I'm a software engineer at Facebook. I've been working in the data center power management space for the last 3.5 years. I'm joining you on a beautiful rainy day here in Vancouver, Canada. As Sulal explained, power outages impact many critical services at Facebook. As an example, I'll be illustrating how power outages affect the Facebook's user database system and the associated user visible impact. Facebook's user database is backed by a MySQL system. It stores all user data, including Facebook posts, likes, and comments. Let's have a brief look at the architecture. Data is sharded and replicated on the user database. We have a simplified example of a single MySQL shard on screen. Every shard hosts data for a subset of all Facebook users. It has a single primary and multiple secondary instances. Note that the primary and secondaries are geographically distributed across different data centers to ensure benefits such as fault tolerance and low read latency. Now let's walk through the database's read and write flows. MySQL directs all user read actions to either a primary or secondary since data is replicated across all instances. However, it directs writes only to the primary. Upon receiving a write, the primary first persists the data to its own local storage and acknowledges the write back to the user. Then it asynchronously replicates the data to the secondaries. Since the primary is essential to ensure that the shard's users can perform writes, let's inspect the impact of a power outage on the database's primary. When the rack hosting the primary loses power, its batteries begin discharging. Once the batteries run out, the primary instance is lost. Users belonging to the shard are unable to write in this state. Recovery is automatic from log backup units or LBUs. LBUs store a backup of all transaction logs on the primary. Every primary synchronously logs all transactions to at least one of its LBUs whenever they receive write requests. After a primary outage, the secondaries notice that they are unable to send heartbeats to the primary. In response, the secondaries initiate a promotion sequence and elect a healthy secondary as the new primary. The chosen secondary catches up to the latest updates on the LBU. Hence, the LBUs prevent data loss after an unplanned primary outage by participating in the promotion sequence. Once up to date, the new primary begins processing write requests. The promotion sequence as a whole takes on the order of tens of seconds, during which time millions of users are unable to perform write actions like publishing posts, liking, or commenting on the Facebook application. This is a suboptimal user experience. In the 2017 power outage that Sulabh described earlier, even the racks hosting LBUs lost power along with the primaries for many shards. Without LBUs, we couldn't guarantee promotions without data loss. Hence, we were operating these shards in a read-only mode. Users hosted on these shards couldn't publish posts, like, or comment for many hours until the power was restored on their respective primaries. They could only browse the app. Up next, Sola will describe the power loss Siren system and how it mitigates power outages. Over to you, Sola.
Thank you, Raghu. Powerless Siren is a system that we have built to broadcast any impending power loss to servers and services within a rack. In a server rack, we generally have a top-of-rack switch at the top that connects all the servers among themselves and to the outside world. There are many servers within a rack, and we also have power supplies and batteries. Power supplies convert the input AC power to DC power, while batteries are used in case of AC power loss. Power loss Siren primarily comprises of two sets of programs, relay and handlers. Relay is a daemon that we run on all top-of-rack switches, while handlers are daemons that we run on all the servers. Now let's look at the flow of events, what would happen during an actual power outage. If the AC power to the rack is lost, then the entire rack runs on batteries. As mentioned before, all our batteries are designed for 90 seconds of backup power. Now, if after 45 seconds, if the power isn't restored, then the power supplies will signal the top of rack switch that there's an impending power loss. We wait for this 45 seconds because it's the SLA for backup power generation. For example, during maintenances, there are open transitions as I described earlier. Similarly, if the utility power fails, we go to a backup diesel generator, and this takes about 10 to 15 seconds. All in all these cases generally finish within 45 seconds. So if after 45 seconds the power isn't restored, then it's almost certain that it's a power outage, and that's the signal that the power supply is sent to the top of rack switch. The relay daemon that's running on the top of rack switch is continuously monitoring for this signal, and once it receives, it immediately broadcasts that signal to all the servers within the rack. The handler daemon that's listening for these alerts picks it up and execute mitigation handlers that are specific to services that run on these servers. Finally, the services then take proactive mitigating actions and this gracefully shut down before the service go down. An important thing to note here is that the entire flow of detection and alerting happens local to the rack, and we don't depend on any external dependencies. This allows us to have a highly reliable signal with very low latency. Now I'll hand it back to Raghu to talk about how services can leverage power loss Siren to be resilient to data center power outages.
Thank you, Sulabh. Now let's analyze how power loss Siren mitigates the impact of power outages for the Facebook user database system. To recap, every shard has one primary and multiple secondary instances. MySQL directs all writes only to the primary instance. The primary persists the data to its local storage and asynchronously replicates it to the secondaries. If a power outage occurs on the primaries, users hosted on the shard can't perform write actions like publishing posts, liking, or commenting. In response to the primary outage, the secondaries will initiate a promotion sequence to elect a new primary. The promotion sequence takes tens of seconds, after which users can resume writing. Now let's inspect how power loss Siren preemptively mitigates power outage on a primary. Again, once the rack loses power, batteries begin discharging as before. However, when no backup power is restored, power loss Siren broadcasts alerts to all services on the rack to take mitigating action. Upon receiving the alert, the primary starts a live promotion sequence. It picks a healthy secondary as the new primary and sends all pending updates to it. The live promotion sequence removes the need for multiple failed heartbeats from the secondary to the primary to ascertain the primary's outage. This reduces the total promotion time. Also, while the promotion is in progress, the old primary is still alive and is able to process write requests. Once the chosen secondary catches up to the latest update, it takes on the role of the primary and starts processing write requests. The only downtime involved is the time taken to switch roles from the old to new primary after it is up to date. Our front-end caching layers have write retries which ensure writes don't fail during this minimal downtime. Hence, with power loss Siren, power outages on the database's primary is completely transparent to the users. Now, let's briefly look at other service architectures that benefit from power loss Siren. To recap, we already discussed primary promotions on single primary databases. For storage services, power loss Siren is used to flush volatile memory structures like disk caches to improve I/O efficiency. More generally, power loss Siren is also used to route requests away from servers that are about to lose power. This is particularly useful for stateless services since any service instance can service all requests. Please refer to our accompanying blog post for more details about each of these different applications of power loss Siren. So far, we have discussed how power loss Siren improves service reliability and efficiency during unplanned power outages. Up next, Parimala will join us to discuss how power loss Siren helps us simplify physical infrastructure management at Facebook data centers. Over to you, Parimala.
Thank you, Raghu. Hi, my name is Parimala Kondeti and I'm joining from my home in California Bay Area. I'm an infrastructure program manager here at Facebook and I've been here close to 4 years. Now that we have seen Sulabh and Raghu explain power outages and PLS in action, let's look into how PLS is helping in simplifying infrastructure management at Facebook. At Facebook, we've historically had dual powered rows. These are rows of server racks that have two power sources, as we can see here at the bottom right corner. These rows host critical services that cannot tolerate a power outage, and there is always a backup power source in case the primary source fails. Let's look at the architecture of the dual powered row. We have the same power delivery hierarchy from MSB down to RPPs, except that the dual powered rows are fed by two RPPs. And if primary RPP experiences an outage, the power is automatically switched over to be fed by the secondary RPP. Dual powered rows can only sustain failures at their SB or RPP level. If it is at the MSB level, a dual powered row won't help because MSB is the common point of power delivery for both the power sources. Now, with PLS, we don't need dual powered rows because we have a high reliability signal into the power loss before it actually happens. So, we remove the need for dual powered rows from our data centers. This unlocks a bunch of benefits from our infrastructure management. As we can see here, firstly, there is no heterogeneous rack and power planning. So racks can be placed in any space instead of critical services only having to be placed in the dual powered racks. So we have better service distribution and hence improved fault tolerance. Let's look at the advantages with this approach. The reason this is very important for us is we have buffers in our data centers where we have extra server capacity to tolerate any one of the power devices outage. Now, with the dual powered architecture, if an MSP was experiencing an outage, we would lose an entire row of critical services and we would only have one row of buffer capacity. But when we have uniform spread, any of our power devices outage cannot cause a significant capacity outage. This means we have not just improved efficiency, optimized placement, but our buffer requirements are also significantly lowered. So far, we've looked at a brief overview of impact of power outages, the design of PLS system, how it simplified both services and infrastructure management. Now let's look at how we evolved our services to get to this place and our learnings along the way. First thing is power outages are a major cause of server downtime, and as the fleet grows, outages become more often because there are more devices that can fail. Second, we are reusing rack batteries, and this has been a much more efficient approach for us because it leads to homogeneous fleet, lower buffer requirements, and simplified service management. Third, we know that the power outages are random events which occur at different scope. To ensure the health of entire PLS alerting and client services mitigation is reliable at large scale, we have set up regular power loss simulations where we simulate our power devices outage and ensure reliable testing, thus making sure that the power loss handling runs well on test instances of all of our client services. So, what's in store for PLS in the future? So far, we described a few examples of services who are PLS clients, and now we are onboarding more services onto PLS. One such example is our storage service. We are using PLS as a mechanism to flush data during power outages for our storage services. This also improves the input output efficiency. PLS is currently only able to handle an outage up to the size of an MSP having a 45 seconds of battery support. But in the future, we expect to experience larger outages because we are deprecating our data center backup generators. So, to enable handling large scale outages, we are building batteries with larger capacity in our future generation of racks. This brings us to the end of our presentation. We have a detailed write-up about this on our accompanying blog post. So please read and contact us if you have any questions or would like to learn more. Thank you.